Hi, this is our presentation for CSC 434, Artificial Intelligence and Machine Learning at SUNY Brockport. My name is Cameron Goldberg. The other group members were Brandon Strong, Matthew Lane, and Troy Cudzillo. We worked with an AI to detect pneumonia using X-ray images. Pneumonia is an infection in the lungs caused by bacteria or a virus. It inflames the air sacs within one or both lungs. Eventually, these air sacs may fill with pus or fluid, causing coughing, fever, chills, or difficulty breathing. A big step in diagnosing this illness is by taking an X-ray of the lungs to examine how they look. The diagnosis involves inspecting the lung in the X-ray to find spots with more white spots in the lungs. This is due to the reflection from the fluid that collects within the lungs. In order to detect this with AI, we're using a convolutional neural network. By analyzing X-ray images, we were able to train an AI to detect pneumonia. This can determine if someone has pneumonia or if they are normal or healthy. But to take this further, we can also detect if the pneumonia is viral or bacterial. The data set we used was taken from Kaggle. It's a great resource for data sets. The data set, it was already annotated for normal bacterial pneumonia or viral pneumonia for each image. The data set was also broken up into a training set, a validation set, and a test set. And in all, we have over 6,000 images in this data set. Our project source was borrowed from an article written in 2020. It is doing pneumonia detection using a CNN and is implemented in Python. It's a really good article. It steps through each section of the code to give explanations along the way. And we were fortunate to find the source because we were able to take that code, load it into our own projects, and get it running without too much hassle. So it was very good. We had a few goals to get done with this project. We wanted to take steps to improve the base project we had found by researching the packages it was using and the tools it was using, and finding ways to tweak these tools and packages to end up getting better results through experimentation. We also wanted to explore other ways of completing the same task of pneumonia detection by finding other tools for AI and other resources. And lastly, we wanted to implement a GUI so that any user can load in an X-ray image and have the GUI prompt the user with its diagnosis. Our first step was to get the AI working. This took some time, but each of us were successful in placing the code into a project. We all used PyCharm to do this, and we're able to run the base project and get similar or identical results. Following that, we all compared the output on our graphs and confusion matrices. And our third step was to improve the accuracy of the AI. Each week, we were all responsible for testing a different change to the program. We all tried different optimizers, different activation functions, and different image transformations. Brandon was very successful in creating a loop that trained the AI using several different variations on image transformations, changing the layers and the neurons. We also ran kernel size, pool size, and filter size under the loops. These loops created a huge amount of data to look at, which was very hard to read. So I ended up being in charge of organizing the data. I did this by writing a Python program to parse through the information and organize it in a way that was easier to analyze. From this, we were able to find the optimal way to train the neural network based on these results, and it allowed us to find a better model. Next, we began working on the GUI. This was Matt's project. He ended up creating something very appealing, very usable. The GUI started out using tkinter, but he found using Qt Designer was a more efficient, user-friendly way to create a nice GUI that ended up being user-friendly as well. Following this, we wanted to explore different packages, and Troy was very vital to this. It was challenging to get one project running, so getting another was a great feat. He ended up going through even another course through Coursera to learn more about AI and using this specific package, PyTorch, is what the project was using to run. So we got that going, and we all did a great job of recording and sharing our results. I was in charge of writing the bulk of the report, and everyone was excellent for providing feedback and editing, and we all chipped in a great deal on this presentation. And here are the packages we used.
All right, so here's the list of settings for the base case setup. As you can see, the image size was 200 by 200. We had 2 hidden layers, the activation function ReLU and output layer with softmax, and so forth. We would later go on to manipulate these values to see how we can improve the AI. So before diving deeper into the presentation, I'd like to explain what this confusion matrix is all about. This is how we calculated our trinary and binary results, along with any false negatives and false positives. Trinary results refers to the bacteria pneumonia, viral pneumonia, and normal classes. However, we determined that we may be able to get a better accuracy if we combine both bacteria and viral pneumonia into just a pneumonia class, making our results binary in nature. We also want to minimize any false negatives because that is the worst case scenario for any patient to be sent home who has pneumonia but was diagnosed as healthy. We also have developed strictly binary AI as well to determine whether someone has pneumonia or is healthy. Okay, so here is our base case results. The first graph with the accuracy, sensitivity, and specificity values. The orange line is the test set and the blue line is the training set. The middle graph is the confusion matrix with the positive and negative predictive values and also the binary accuracy. And the graph on the right is the loss graph. Obviously, we want to minimize loss and maximize accuracy. And here are our binary results that we got from changing outputs of the convolutional neural network to 2 instead of 3. As you can see, the results from the base case are 80.61% accuracy, and our binary accuracy was 86.06%. After viewing these results, we began to brainstorm some ways to improve accuracy, including best number of epochs, changing size of images, changing the padding on the images, different stride values, among many others that are listed here. So we actually wrote some loops on base case settings to change height, width, zoom, and rotation. We would go on to save the confusion matrix, accuracy, and loss. But as time went on with the project, we drastically improved our hypothesis on how to develop better accuracy. So here is the image generator settings that we would manipulate via the loop. We would start the loop to change the values by 0.1 after each iteration, and the variables changed were rotation range, zoom range, width shift range, and height shift range. And we also have listed here what 2 settings we found to be the best and their accuracy percentages. Then we wanted to determine the best epochs. We ran different epoch numbers on base settings, best image generator settings, and second best image generator settings. And we found if the program was saving at the end of the training, that the best epoch range was like either 90 or 120. And listed here are 3 accuracy score graphs after 150 epochs. And as you can see, overtraining occurred on the first graph using our data variables. And here is a list of optimizers we tried throughout this project. We found the best optimizers to be AtomMax, Atom, and NAtom. And ultimately, we found the best optimizer to be NAtom. And here is the optimizer results between AtomMax and Atom. I mean, there really isn't too much of a difference here, as you can see. However, after further research online and using other resources, the general consensus is that Atom is the optimizer to go with.
Okay, so now let's go over the resizing of the image results. So we started from pixel size 50 by 50, and then we increased it by 25 after each iteration. We ended it at 500 by 500, and on the right here we have our best accuracy. As we can see, the first accuracy is the best at 50 by 50, and 100 by 100, and so on. Okay, so now let's go over the number of neurons and the layer results. So the steps to do this. First we started with one layer at 10 neurons, and then we increased by 10 neurons after each iteration. We kept doing this until the GPU ran out of memory. At that point we would pick up the best accuracy rate for that layer and the neuron. We would keep those neurons for that layer, and then add another layer starting at 10 neurons as well, and then loop through and do the same process. An example of this is down below, where we have layers 1 through 6 with different neurons. So layer 1, our best neuron count was 150. Then we added another layer that added 10 neurons each iteration, and then we found the best accuracy for those 2 layers, and then continued. Our best combination of layers and neurons turned out to be 2 layers, the first layer with 150 neurons, and the second layer being 610 neurons, and this resulted in an accuracy of 87.66%. Okay, so now we have the padding results, and there are only 2 options for padding, and on the left we have valid, and on the right we have our base case. And looking into them further, there really isn't a difference between the 2, so we decided to roll with the base case. Activation function time. Alright, so let's start with the obvious here. There are 4 graphs here: exponential, SALU, ftmax, and ft-sine. These 4 graphs did terribly. There is no variation at all went through any of the training. So these are going to be immediately excluded. We're not even going to consider them. But the other 2, ELU and FTT+, they did decently well. ELU was around 70%, and FT+ was around 85%. Okay, so now we have activation functions. We have 3 more of them. And sort of like the last one, we have 2 of them here that are, again, we're not even going to really consider them as they didn't even change throughout any of the training. But then we have our ReLU, which is actually what the base case was for the activation. And again, that's around 85%. So in the end, we decided to go with ReLU because it performed well. Alright, so let's move on to the stride value results. We decided to do the strides from the value of 1 through 10, and it turns out that the stride values starting from 4 to 10 return an error, and the strides from 1 to 3 worked, and our initial base case value of stride of 1 returned the best percentage of accuracy. So we decided to roll with that. Now time for the biggest results that we have run, and this is filter size results. So we actually ran 811 iterations of this AI, and we went through all 811 accuracy graphs, and we picked the best filter size out of all of them, which happened to be filter size 12 and filter size 14. And under these highlighted parts here, you can see the numbers of where they actually changed in the AI. Kernel size results. So this one we didn't run nearly as many iterations because we were running lower on time. But we ran through 54 iterations, and this is when we started saving the model with the best loss. And then we also implemented creating a program to auto-compute the information from the models. And to further elaborate on this, what we have here under model info, this is everything that the program is creating automatically after saving each best image. Okay, so much like the kernel size results, our pool size results, we also ran 54 iterations of the AI, except this time we saved the model with the best accuracy instead of the best loss. And everything else was the same, so our best pool size that we calculated was 8 and 9. And here are the different packages for PyTorch. Alright, so now we have the PyTorch test set results. On the left we have the trinary results, saving with the best loss, and on the right we have the binary results, saving the best loss as well, both of them at 120 epochs. The trinary result had a terrible amount of false negatives at 37, probably the highest we've seen yet. The binary accuracy though was quite high at 89%, and the normal accuracy was 81.41%. Now the binary accuracy was at 87.82%, and the false negatives was at 30. Still a terrible false negative count, but it's interesting to see that the binary did worse than the trinary with the binary added by 2%. Just something to note.
At the completion of each run, TensorFlow would present us with a series of graphs showcasing its performance, such as the accuracy score and the loss value. Additionally, TensorFlow would produce a confusion matrix showing the performance of the run, and on the right, those are our combined statistics for that run. And here we showcase the performance of one of our binary networks.
After being met with initial success with our models, Dr. Yu encouraged us to expand the breadth of models that we used with our project. And as you can see, we found several settings and configurations that were suitable for us. As you can see here, here's a brief overview of the performance of our networks when tested against the validation set. This is in contrast to the performance of the base model, which, as you can see, we've greatly outperformed in several cases. Early on with our project, we were unclear as to whether we'd be able to contribute in a significant way insofar as improving the accuracy and performance of the existing models. So we decided that we would like to take this project and give it a practical application, and that being to be used as a diagnostics tool for the evaluation of X-ray images to determine whether or not patients had pneumonia or not. We felt that this would allow doctors, nurses, and clinicians to quickly and easily identify, or at least use as a tool to assist in identifying pneumonia. And we believe that we have accomplished this, and there will be a short demo in the next slide.
So we have 4 models for TensorFlow and 2 for PyTorch, and they're split among these presets. So let's start out with the default interface, which is what the user is greeted with, and this is a stock image that's referenced in our references slide with a helpful message to please load X-ray. Now, if the user attempts to load an image but cancels it, they'll be presented with this error message. Now, after successful loading of an image, the relevant network will start to load, and subsequent runs will also run on the same settings. So there is an initial please wait message there, but as I load additional images, the next image will load almost immediately. All right. So in addition to that, we've got some settings for having low false negatives. So let's try one of those for TensorFlow. Okay, 96%. And we'll do another bacteria with a 97.91% certainty. Well, if we were to say load an image that was primarily white space, it would attribute that to having pneumonia. And in this case, it's quite confident to be in 100% that this white image has pneumonia. And even some of our test data sets, as you can see, it's critical. This patient definitely has pneumonia. And so does this one, unfortunately. Might have to tell its folks. But bottom line, the idea being that this product is going to be a useful tool to supplement the tool set that doctors and clinicians have, but it won't be replacing them anytime soon. That being said, thanks for watching the demo and continuing on with the presentation.
Without going into extraneous detail, there were several things during our project that we could have improved on had we known or had the benefit of hindsight. One of the things that stands out early on is the delay for leveraging the GPU technology. We simply were unaware of how much it would benefit. For example, each TensorFlow epoch was taking between 1.5 to 1 minute 45 seconds versus under 30 with the CUDA architecture. And once we had leveraged that with PyTorch, data collection with that network was so much faster than our initial foray into artificial intelligence. Here are some image references for resources we used throughout our project. Thank you so much, everyone, for your time today. as well as Dr. Yu for the encouragement and support throughout this project, as well as the Computer Science Department of Brock